Okay, so we are starting lesson B of 5.1, which deals with specific forces, specifically force of gravity, the normal force, friction, and tension. So those are the main forces that you will see and consider in most problems. So the force of gravity, which is represented by a capital G here, that's different from the acceleration gravity, which is little g, is just your weight of your object. So it's how much an object weighs. It's dependent upon this formula, which is big G for the force of gravity is equal to mass times little gravity. So m is mass, little g is the acceleration due to gravity, and that's all spelled out for you down here. So you just need to know the mass of an object and the acceleration due to gravity. If we're on Earth, it's 9.8. So if this is the Earth, that's a bad drawing of the Earth. So let me use a tool here to make a circle. So if we have the Earth here and an object is on the Earth. So let's say we just have a person standing here. The force of gravity is the weight of that person. So it's how much a person weighs or that object weighs. And it is always directed towards the center of the Earth. So it's pulling, in this frame of reference, down. If you're on the side of the Earth here, there's a person standing maybe at the equator. This person's huge again, but just to give you a frame of reference or the idea, it is always pulling towards the center of that Earth, not as just equal to this equation. So if you're on the Earth, use 9.8. Sometimes we'll talk about the force of gravity between objects besides, say, an object and the Earth, but between two separate objects, and we will use a different equation. You'll learn about that in the next week's videos and activities. So force of gravity, pretty simple equation, G equals mg, and in our frame of reference, it's mostly just pointing down. Okay. The next force we're going to figure out is the normal force, and the normal force is represented by a capital N, and it's the force that acts perpendicular to a surface. So it stops an object from penetrating into another object. So when you push on anything, the normal force is what prevents, say, your hand from going through that object. So we're going to go through this example here. There is no formal equation for the normal force, so you have to essentially find it through kind of analyzing the situation. And the normal force basically balances the external force. So whatever force you apply, the normal force is, or whatever multiple forces can be applied. The normal force is what's creating a force to counteract those forces. So, in this example, it says, what is the normal force acting on a 10 kilogram box? So this box is 10 kilograms. So 10 kilograms would be its mass. So right above the 10, so we know that. And if we were drawing a free body diagram with the arrows here, we're going to use the drawing tool to help a little bit. So if we think about the forces acting on this object, we have the force of gravity trying to pull it down. And again, I'm just going to label that with a G. Type. So that's just G. So that's the force of gravity trying to pull down. And what is stopping the box from falling through the floor? That would be the floor itself. So the floor pushing up provides a normal force. So I'm going to change colors here so it looks different. So just change to like green. And the normal force has to go up and has to counteract it. Now, if the normal force was really big, and that arrow and green arrow is obviously bigger than the black arrow, what would happen? It wouldn't behave the way that we would want it to, and this box would accelerate upward. If the green arrow was too small and it was going up, then that wouldn't work either, because it is canceling out that it isn't canceling out that whole gravity force. But if we have it so it is exactly balanced, which is what we want, these two arrows should be canceling each other out, and that would be the normal force. So in this case, the normal force is providing a force to balance the situation. And as long as they are balanced, this would just stay stationary like we would expect. So we're going to practice a little bit of calculating on both these. So to calculate G, we would use the formula mg. So if we had 10, and it'd be times 9.8, and that would be 98 newtons going down. So it's directed down, and I would put a negative sign here because the force of gravity is pointing down. For the normal force, in order to balance it out, you would say, okay, And this is where a lot of times I told you guys to set up tables. So in our chart, we got the forces, we have gravity, we got the normal force. Those are the two arrows that are in my picture. And gravity is negative 98, which we just calculated. This is in the y direction if you want to write y. And then 98, take out that accidental dot there. That's going down. Our net force, which is the sum of these forces. So when I put all these forces together, I get my net force, which we talked about when we were describing, say, the broom ball activity or the hover puck example. So that's 98 there. This is 0 because the box is not accelerating upward, it's not or downward, it's not changing its motion, it's just staying at rest here. So if this is 98 going down and we get 0 for the net, the normal force also has to be 98, but it's going to be positive this time. So this is a positive 98. So we had just calculated the amount of normal force acting on this box, and you can see it balances it out. That's the key. Let me pause a second here. So so our normal force and gravity force balance out. You don't always have the same amount of force every time. So like you don't always just have one force where the gravity and the normal force are always equal to each other. So let's try this situation. So it says, what is the normal force acting on the 10 kilogram box this time if I push down on it with a force of 10 newtons? So if I was drawing my free body diagram in this one, so we'll draw the arrows. We have a gravity force still, and that gravity force is still going to be 98 going down, so that didn't change. And now I'm going to push with another 10 newtons of force. So I have two forces going down, my hand pushing down on it, which I'll label force of hand. That's equal to 10. So we get the force of the hand pushing down, which is 10. And we have the gravity force here, which is still going to be 98. I'm going to leave out the negative going down here in my my little arrows. I'll put them in the chart. I'll shrink this a little bit if I can. So I have both of those forces going down out, and then the normal force, which is our force that we're going to draw going upward, it has to balance out both of those now. So when I draw this force going up, these two together are getting canceled out by our arrow in green there, which I described as my normal force. So so really we're looking to try to figure out, all right, how much normal force do I need? So because I pushed more downward and the box isn't moving down, that means the floor or the surface is pushing more upward. So again, we'll set up our table and try to figure this out. So the big difference here now in this one, again, is that we're just dealing with the y direction. If we had multiple directions, we could write an x over here, but we have our gravity. We have the hand, so I'm just writing F and then a little subscript of hand here for that. Ooh. And then we have the normal force. When we add all this together, we get the net force. Again, if you're thinking about this situation, this is balanced because the box is not accelerating, it's not speeding up, it's not slowing down, it's not changing direction. So the net force is 0. And we've said that gravity is down and hand is pushing down, so those are both negative. This is 98. And this is 10. as I push with an additional 10 newtons of force going down. So this normal force going up has to balance those out. So if I put those two together, 98 and 10 together are 108 going down. So the normal force would need a positive 108 going up to make this work. So so that is the normal force in that situation. That's the answer. So the normal force got bigger because we pushed down. And the opposite would happen as well. So I'll maybe not show as much kind of math here, but you get the idea. So this time we have our arrows and we still have our 98 gravity arrow going down. Don't make that too big. So that's 98. This time the hand is pushing up. So the hand is going up with 10. And the normal force arrow is going to compensate to balance things out again. So change color. So the two upward arrows are going to add together to get to the downward arrow. So again, we said this is gravity there. The upward arrow for the force of the hand, which is only 10. So our force of our hand's 10. The gravity force was 98 going down, and then the normal force, we are trying to figure out how much normal force there is, and that's going to balance everything out. So if I have 98 going down and 10 going up, to balance the rest of it, the difference between the force hand going up and the gravity force going down, that's going to be 88 going down. So the normal force has to be 88 newtons going up. So again, you would use this similar method if you like that chart. I'm skipping over a little bit because I think you guys are getting the hang of it. So the idea is that the normal force just makes it so the net force goes to 0. So if we had 98 down and 10 going up, the normal force has to provide the other 88 going up. That's it. So so those are the ideas with normal force. Again, there is no formal equation like gravity or friction, which we're going to talk about next. But it is a balancing kind of idea. It doesn't always have to be in the y direction. So just to talk about that briefly, it doesn't happen in many situations, but like if you imagine I had a wall and I had a box. Nope, that's not a box. That's a box. And I was pushing with a force of my hand going in on the wall. So if my hand was pushing, say, to the left in this picture, there'd be a force of gravity trying to pull down. Which we could label G. But in order to keep this from moving, so there had to be a force going kind of this way. That's from the surface. The normal force acts perpendicular to the surface. So this would be the normal force going to the right. So that would be the normal force. And it has this gravity force has no bearing on this normal force. So the more I press with my hand pushing into the wall, the normal force would push more going out. It's not related to gravity all the time. In this picture, in order to keep it from sliding downward, there'd have to be a force going up. So let's draw that in. And that's going to be the next force we're talking about. So this, if it was all balanced, this upward force would cancel the downward force, the left force would cancel the right. And this force that is going to be represented here is friction. And friction is represented by a letter, and it's a lowercase f for friction. So We're going to get into that one next. So for friction, there are two types of friction. Friction is a force that acts to prevent sliding. So there are two types. One is called static friction. Static friction keeps things from moving. So it's stationary. It doesn't move with static. And then the other type of friction we have is kinetic friction that slows a sliding object down. The equation is the same for both. So that equation is here as F equals UN. So I just highlighted that. We're going to talk about what those different ideas mean. So F again that's the friction. And we just got done talking about that's the normal force. So you have to figure out the normal force in order to use this equation. And then U is a characteristic of how slippery the surfaces are. So that's something known as the coefficient of friction, which describes again how slippery or rough the surfaces are. If you want friction to get big, if you want this friction value to get big, you would want these two values to get big. So these are directly related. So U, the coefficient of friction, would be large, and the normal force would also be large. If you want the friction to be little or small, you'd make these numbers small. So it would be very little normal force, and then the coefficient or the slipperiness, that would be a low value. The values for U are generally between 0 and 1. Okay, so the higher the coefficient, the bigger this number is, the rougher the value, or the rougher the surfaces are, the more rip or friction there is, and then the lower the value, the less there is. You might have a question about how normal force is related to friction, or why it's related to friction. I can kind of describe that again. So keep trying to push the wrong thing. So I'm gonna take this box example again, and we'll say the box is on a flat surface like the ground, okay, or a table. So between those two surfaces, sorry, but between the box and the floor, right, the table and the box, they seem smooth, but they're not actually smooth. So if you look at kind of the interaction between those and the surfaces, they're actually bumpy. So if you take your hands or knuckles, that's kind of what's going on. So let me draw this. So if we like zoomed in here with like a very powerful telescope, not telescope, microscope, excuse me, the box might be bumpy like this, and the table, which is the bottom surface, that would be bumpy as well. So if you think about your bumpy surfaces, I want you to take your two hands and your knuckles and kind of push them together, right? And then I want you to just try to slide your knuckles against each other. So move one of your hands kind of one direction, going one direction, and then the other hand going the other direction. So the bumpiness, that's like the unevenness in the surface. And if you try to like just gently push your knuckles against each other and rub, there isn't a whole big force locking them in. But if you push them together more, right? So if you hold and you press your two surfaces together, so you push your hands together to represent the surfaces, there is more friction there. There's more stuff holding it in place because you've increased that normal force. So that's the normal force idea in a brief kind of description that you can think about. Okay. So you just use those formulas for those things. So that's it for that. And then for tension, that's the last one. A tension is just a force in a cord or a rope or a string. There is no formal equation again that we're going to deal with. There is one, but you don't worry about it in this class. So it's got no equation. Sort of like normal force, it's there. You can figure it out depending on the situation. Okay, so I'm going to stop there, and then the next video we're going to get into Newton's laws, and that's going to help us solve force problems as well.